Hey guys, in this video we're going to go through the 5-step process for solving any induction proof exercise. If followed correctly, these 5 steps should put you in a perfect position for scoring the maximum number of marks in an IB exam on induction proofs. Now, the first 3 steps, they're quite easy. There's no excuse to miss those marks. The fourth one depends on the type of induction proof that you're tackling. Therefore, we're going to go through 2 different exercises, 2 different examples to show you how that fourth step would change or will change. And on the fifth one, we have the conclusion, which is also composed of very easy marks. You just have to spit out the answer, to vomit the answer. The conclusion looks pretty much the same. It doesn't matter which type of induction proof you're solving. So let's get to it. Let's get through these 5 steps. The first example is one that involves series. This is actually a proof for the sum of the first n+1 terms in a geometric sequence, one in which u1, the first term, is equal to 1. So what are these 5 steps? Number 1, we need to write the propositional function. Therefore, we're pretty much copying what the exercise has asked us to do. Step number 2, the base case. Notice where your interval starts. Right now we're talking about positive integers, therefore the interval starts at 1. So on the base case, we're going to evaluate the left and the right hand side for n equals 1. Now in this case, be careful with the left hand side because n is equal to 1 over here, meaning that for n equals 1, on the left hand side we have 1 plus r. Now on the right hand side, we are going to replace 1 into n, which gives us r squared minus 1 over r minus 1. And knowing the formula for the difference of 2 squares, what we get is also r plus 1 as expected. When you get to this phase, you're going to realize that the base case can be proven, otherwise there would not be any induction proof exercise. Therefore, you have to state that you got something that's true. Left hand side is equal to right hand side, therefore base case holds. Now step number 3. The inductive hypothesis. This is also a place to score easy marks. You're pretty much copying your P of n, but substituting your n's by k and stating that you're going to assume that this is true for some, and then you write down the interval. In this case, positive integer k. Now onto the hardest part, which is the inductive step. Now, this is the only part in an induction proof exercise that changes based on the type of induction proof that you have. If you're tackling an induction proof with series, which is this case, you have some particular recipe. If it's with divisibility, it's something else. If it's inequalities, it's something else. Therefore, we're gonna go through 2 examples in order to show 2 different types of inductive step, which is the 4th step of the solution. And in other videos, we'll detail even more all other types of induction proofs. But just for the sake of talking about this 5-step process for solving induction proofs, we're going to keep it with 2 examples only. So let's tackle the 4th step in this process. In P of k plus 1, you're rewriting P of k, but going 1 iteration more on the left-hand side and substituting k plus 1 in the place of k on the right hand side. So what we have is r to the k plus 2 minus 1 over r minus 1. Now, the way to solve induction proofs with series is we start with the left hand side of P of k plus 1, and by replacing P of k, we need to get to the right hand side of P of k plus 1. So the goal is to get here. So we're going to start from here, and knowing that the sum of these terms is equal to r to the k plus 1 minus 1 over r minus 1, we're going to work our way to the right hand side of P of k plus 1. Now let's see if we can get there. I'm going to put r minus 1 as a common denominator, so we have r to the k plus 1 minus 1 plus r to the k plus 1 times r minus 1, which by foiling we can see that it's the same as r to the k plus 2 minus r to the k plus 1, and we still have that r to the k plus 1 minus 1 on the left here. Therefore, these guys cancel out, And we have r to the k plus 2 minus 1 over r minus 1, which is indeed equal to the right-hand side of p of k plus 1. Now, the hard part is done. All that is left for us to do in this example is to write the conclusion. And the conclusion has a predefined mode. You're going to write, given that p of 1 is true because p of 1 was your base case, and that p of k plus 1 is true whenever p of k is true for some positive integer k. By the principle of mathematical induction, you can write PMI, that's fine. P of n is true for all positive integers. And there you have it. These are the 5 steps in solving any induction proofs exercise. Number 1, writing P of n. Number 2, base case. Number 3, P of k, which is the inductive hypothesis. Then we move to the inductive step. And lastly, we write the conclusion. Now we're going to do the same with another example, which involves divisibility. All right, so now that we just finished the first example, let's move to the second one, which is one that involves divisibility. It is considered to be an easier type of induction proof, so this will be faster. And the second example is the following. Use mathematical induction to prove that n cubed minus n is divisible by 3 for all positive integers. Now, I copy the 5 steps over here because they're not going to change. However, step number 4, which is the inductive step, will be different in the way that we approach it. We still have to go through that step, but it will feel and be different. So how do we carry out an exercise with induction proofs and divisibility? Our P of n is going to be n cubed minus n is divisible by 3 for all positive integers. And the base case that we're going to use is with P of 1, given that we're talking about positive integers. Therefore, 1 is the first positive integer, which should be used. So let's start by replacing 1 into n cubed minus 1. So what we have is 1 cubed minus 1, which is equal to 1 minus 1, which is 0, can be rewritten as 3 times 0. Why did I rewrite it as 3 times 0? To prove that this number right here is divisible by 3. In fact, 0 is divisible by any integer, which of course includes 3. So we write which is divisible by 3. So moving on to P of k, we're going to rewrite n cubed minus n as k cubed minus k, and we're going to say that this is equal to 3 times a. Now, what does that mean? A being a positive integer, which can take the place of 1, for example, or 3, or even 7, when multiplied by 3, gives us all these multiples of 3, which means that all of these numbers, they're divisible by 3. So this is a way to represent a number which is a multiple of 3, or which is divisible by 3, which is the same thing. So we're going to assume that this is true. It's important that you actually state this. You actually state that we're assuming P of k to be true. Now on to P of k plus 1. And this step will look different as compared to when we solve an induction proof which involves series. When we have divisibility in an induction proof, what we want to do is to replace k plus 1 into k using P of k as a reference. And at some point, we're going to substitute this into our P of k plus 1. And how do we do that? Well, let's just expand k plus 1 cubed minus k plus 1 first. So we have k cubed plus 3k squared plus 3k plus 1 minus, and this is the minus here, k minus 1. Careful with this sign. You can simplify these ones, and you can rewrite this as 2k, giving you k cubed plus 3k squared plus 2k. Now we can replace k cubed by 3a plus k, and we can replace it over here, given that we're assuming this to be true. Therefore, we have 3a plus k plus 3k squared plus 2k, which can be simplified to 3a plus 3k squared plus 3k, and factoring out a 3, we can see that we do get a number which is divisible by 3. And there you go. We only have to write the conclusion now and we're done. I'm gonna borrow the conclusion from the other exercise because actually it doesn't change at all. Given that p of 1 is true, which is our base case, and that p of k plus 1 is true whenever p of k is true for some positive integer k, then by the principle of mathematical induction, p of n is true for all positive integers. And there you have it. This is induction proofs in 5 simple steps.